Every single second of every single day, the world around us is changing. Sometimes it's spectacular, sometimes it's totally invisible. To really understand what's going on, you've got to speak the language of chemistry. So today, we're going to learn the basics and start decoding the world.
I mean, just look at this. A beautiful, brilliant explosion of light. We see fireworks, we love them, but what's really happening on a tiny molecular level? Well, what you're seeing is a super fast, amazing chemical reaction. And that brings up a much bigger question.
So, what is it? The answer is that all three are examples of a chemical reaction. It's really just a process where your starting substances, we call those the reactants, rearrange their atoms to become totally new substances, the products, with brand new properties.
Now, to describe all these incredible transformations, chemists use a very specific kind of language. So for this first section, let's just think of it as learning the alphabet. I promise it's way simpler than it sounds. Okay, so every reaction has two main players. First, you've got your reactants. These are your starting ingredients, what you have before anything happens. Then you get the products. That's the new stuff that's created after the change. It's just like baking, right? The flour, sugar, and eggs are your reactants, and the finished cake is the product. Now, here's how we write these recipes down. We could use a word equation, which, spells everything out, but chemists are all about efficiency, so they preferred the chemical equation. Here, every substance gets its own chemical formula. That little plus sign means reacts with, and the arrow basically means turns into or produces. And to get even more specific in our chemical sentences, we use state symbols. These little letters in parentheses just tell us what state the substance is in: solid, liquid, gas, or aqueous, which is just a fancy way of saying it's dissolved in water. It gives us a much clearer picture of what's going on. All right, so we have the alphabet. Now we need the most important grammar rule in all of chemistry. This is the big one. It's the one law you absolutely cannot break. And here it is, the law of conservation of mass. All it says is that matter can't be created or destroyed. That means in any reaction, the total mass of all your reactants has to equal the total mass of all your products. Nothing just disappears into thin air. And this visual just shows it perfectly. Look at that scale. The mass before the reaction is exactly 92.95 grams. Then, after the reaction happens inside that sealed flask, the mass is still exactly 92.95 grams. See? Nothing was lost. So why is the mass always the same? Well, this slide shows you the secret. Atoms aren't created or destroyed in a reaction. They are simply rearranged. They're just shuffled around into new combinations, like a deck of cards. The atoms you start with are the very same atoms you end with, they're just holding new hands. Okay, so if atoms can't be created or destroyed, our chemical equations have to show that, right? This is where we learn how to write a grammatically correct sentence in the language of chemistry. I'm pretty sure this meme captures a feeling that every single chemistry student has had. You write out your reactants and products, but the atoms on each side of the arrow just don't add up. This first draft is called a skeleton equation. It's got the right idea, but it's breaking our golden rule. But balancing is really just a simple puzzle, and there are only 3 steps to solve it. First, you take inventory. Count up every atom on both sides of the arrow. Second, you add coefficients. These are big numbers you put in front of the formulas. And remember this, you can never change the little subscript numbers in a formula. Finally, just check your work to make sure it all adds up. All right, let's walk through 1, magnesium reacting with oxygen. Our skeleton equation is Mg plus O2 yields MgO. So let's take inventory. We have 1 magnesium on the left, 1 on the right. So far, so good. But we start with 2 oxygen atoms on the left and end up with only 1 on the right. Uh-oh, an atom vanished. That breaks the law of conservation of mass. So how do we fix it? We add those big numbers, the coefficients. Let's try putting a 2 in front of the product, MgO. Okay, that gives us 2 oxygens on the right, which is great, but now we have 2 magnesiums there. No problem. We just hop back to the left side and put a 2 in front of the Mg. Now let's recount. 2 magnesiums on both sides? Check. 2 oxygens on both sides? Check. Perfect. It's balanced and our puzzle is solved. Awesome. Now that we know how to write a perfectly balanced chemical sentence, let's explore the different kinds of stories these sentences can tell. You can think of it like there are 5 main genres, or personalities, of chemical reactions. Let's start with two that are literally perfect opposites. A synthesis reaction is when two or more simple things combine to form something more complex. It's like building something with Legos. And decomposition? Yep, you guessed it. It's the exact reverse. One complex thing breaks down into its simpler parts, taking the Legos apart. Next up is combustion, which is really just a reaction with oxygen. This can happen slowly, like when iron rusts, or it can happen super fast, like when natural gas burns. And here's a key tip to remember. When a hydrocarbon burns completely, the products are always carbon dioxide and water.
Our next type is single displacement. And the analogy for this is perfect. Imagine element A is dancing all by itself, and B and C are a dancing couple. In this reaction, A cuts in, kicks B out, and forms a new couple AC, leaving poor B all alone.
But wait, there's a catch. This dance doesn't always happen. There's a rule book called the activity series, which ranks metals by how reactive they are. For our lone dancer A to cut in, it has to be more reactive or higher up on the list than B. If it's lower on the list, sorry, it's not strong enough, and no reaction happens.
So if single displacement is one dancer cutting in, double displacement is when two dancing couples meet on the floor and just decide to swap partners. The first part of each couple, A and C, trade places. So AB and CD become AD and CB, a total partner swap.
Now, double displacement has a couple of little surprise twists you have to watch out for. Sometimes one of the new couples you form is unstable and immediately breaks apart. If your reaction makes carbonic acid, for example, it instantly decomposes into water and carbon dioxide gas. Same for ammonium hydroxide. It becomes water and ammonia gas. So you got to watch out for those. So we've learned the alphabet, the grammar, and the main story genres. We're starting to get pretty fluent in the language of chemistry. But why does any of this actually matter outside of a lab?
It matters because this language describes everything. It's the synthesis reaction that's powering your phone battery right now. It's the decomposition happening in a compost bin. It's the combustion firing inside a car's engine. Chemistry is constantly telling stories all around us. The real takeaway is, now that you know the language, what stories are you going to